Welcome back, and welcome to the final section of Calc 3. Right, in this next set of videos, and there's going to be quite a few, we'll cover topics from vector calculus. Right, and this is really the pinnacle of Calc 3 here. This is, in my opinion anyway, what we've been working towards the entire time, doing the partial derivatives and the multiple integration and all that. The goal is to get here. Right? This is where physics can start coming in. I mean, we already had some physics before, but this is where we can really start saying something interesting. Right? But in order to do that, we need to develop the tools of the trade. Right? We've been dealing with scalar valued functions so far, but that's not really going to cut it. Because think of, for example, having a planet. Right? Planets have gravity, right? And it pulls things essentially towards the center of the planet. Or even better, think of the sun. It pulls all the planets inward towards its center. And it doesn't matter where around in space it is, it's going to pull basically just according to the masses of the sun and the object and the distance between them, right? But it describes something on all of three-dimensional space, and then it gives you a direction in which it's pulling it in three-dimensional space. So we need a function that's going to take three variables and give us a three-dimensional vector. Right? And this is where vector fields come in. So let's start by defining what a vector field is. Right? So definition. A vector field let's start with R2, is a function like this, f, and we'll give it the arrow of x, y. This is going to output a vector with two components, both of which depend on x and y, right? Or you could write this, if you like, p of xy I plus q of xy j. Right? Either one. It doesn't matter. Whichever you like. Okay? So that's a vector field on R2. All right? So it takes a point in the domain of R2 and it sticks a 2D vector on it. All right? But what about on R3? Well, it's a function that takes in a point from 3D space and spits out a 3D vector. Right? Right? And the three components of that vector all can depend on the point you plug in. Right? And a great example of that is going to be this thing about gravity I was just talking about. It's going to depend on, all three components are going to depend on where in space you are. Right? Because you're always being pulled directly towards the center. All right. So, and again, you can write this as, pi plus qj plus rk, of course. Right? So this is what a vector field is. Right? It's basically a function from R2 to R2 or R3 to R3, more or less. Right? Something we can say is these guys here, we call those component functions. Right? So perhaps that's not such a surprising name. Right? Since components of a vector, there's functions in those components of the vector, so they're component functions. Probably not a big deal. Okay? So what's an example of these? How do you graph a vector field? So the way one typically graphs a vector field is the following. So we'll do some examples, some hand-drawn examples, and then in the next video we'll do a few more examples that are in Mathematica, because it's especially hard to draw vector fields in 3D. All right? So let's go ahead and say example, and let's start by graphing f of xy is, what do I want to use? Minus 1 and 1. Right? So how do we sketch this guy? Right? So loosely, the idea here is we have the xy plane, and what we're going to do is at every point of the xy plane, we need to stick this vector, negative 1, 1. Now, of course, you might imagine we can't really do that, like drawing it out and put one at every point. That's going to be kind of hard, and it's going to get crowded. So usually what we do is we just take some sampling of points, say something like this. Right, so get a whole bunch of them here. If you're doing it by hand, you don't really need to do this many. So I won't graph all of these, but just take some selection of points here, and then, so if this weren't constant, you could just take the point here and plug it in. But they're all minus 1, 1, and a minus 1, 1 vector goes to the left 1 and up 1. So we get this. So we get something that looks like this. It's a vector field that's always pointing in this sort of northwestern direction. Right? And, okay, so not too bad. Let's do an example that's a little more sophisticated. Say b f of xy equals xy. There's variables in there now. Right? So how do we graph this? Well, it's the same first principle. Right? We're just going to draw some vectors at every point. Right? So it's going to say this is 2 up here, minus, or I'd say this is 1, this is a half, this is minus a half, and this is minus 1. And we'll do the same sort of scaling here. Right? So 1 and minus 1. All right. So what do these vectors look like? Right. Got a whole bunch of these here. What do vectors on this thing look like? So let's sketch a few of them. Right? So if we take the vector here at the origin and we plug in 0, 0, we get the 0 vector. So the vector field is just a dot there. All right? But what about at a point like 1/2, 1/2? Well, then the vector is going to be 1/2, 1/2, which happens to be that. Right? What if we put it in at 0, 1/2? Well, then we get 0, 1/2. That's a vector that looks like this. Right? So we start seeing this pattern show up. Right? But now you could ask, well, what about the vector out here at 1, 0? Well, that one is the vector 1, 0, right? So it goes even further. And I'm getting kind of out of control here, and oh, that's off the board, so you can't see it. But then, you know, like here, this point, negative 1/2, 1. So it's going to go to negative 1/2, but up 1. Right? And you're going to have a similar thing here. 1 comma a half will go 1 up a half. Right? So you kind of get the idea of what's going on here. At every point, you're going to have some point x comma y. You plug that into the vector field. That's going to give you a vector, and then you stick the vector on the point. Right, so it gets kind of messy drawing it by hand, and I apologize, this is an especially messy picture here. Let's draw one more vector at 1, 1. You're going to have a really long guy here. Right? So you're going to have this thing that at this origin, they're very, very tiny. Right? But as you go out, they get bigger and bigger. Now, usually when we graph these with, say, something like Mathematica, we don't draw, and even by hand often, we don't draw the vector field or the vectors true to their actual size. Like something Mathematica, I believe, will do is make the vectors bolder as their magnitude gets larger, right? So that's a way to represent kind of this vector. They look all the same size, but one's bolder, so it should really be much longer, right? That's one way to represent it. Another way is to just scale everything down. So like here, this vector, make it half its length, and then all the other vectors get their lengths halved, right? And it just makes the pictures less messy. But that's essentially what a vector field looks like. You have your plane, and you have a bunch of vectors all over it, right? And in a 3D vector field will be, you have your three-dimensional space with a bunch of arrows all over the place, right? So maybe you can kind of visually see now that, say, that vector field for gravity I was talking about. Can you imagine what that looks like if you plot the vector field in 3D? You should see a whole bunch of arrows just pointing in towards the center of the planet or star or whatever. Kind of like the backwards of this, but in 3D. All right? So hopefully this all made sense here, and see you in the next video.